Welcome to my video on homemade sundial observations and time corrections. I'm going to go over some results of some observations I took with a homemade sundial on September 11th, 2025 and explain the corrections to you. This is a picture of my homemade sundial. I've got a previous video which I've got a link in the back that shows how I constructed it. So that's all the details in there, so you can watch that video if you want to build one yourself. In this video, I want to go over the analysis of the results and explain the corrections of all that gets. You need to understand that. So here are my observations. On the left column is the actual clock time. I measured this with my iPhone, so I think that's real accurate. And then this is the actual sundial time that I read off of the dial of the sundial. And there's a bit of an art form in doing this. You just need to be consistent on how you do that because it's hard to tell sometimes where the shadow is. So that takes a little practice. Now the first correction I want to talk about is because your actual sundial time is not your local true time. So what I want to go over is explain this first one is called the equation of time correction. And it's over the course of the year, sundials that show true solar time do not always match up with the standard clock or mean solar time. And the difference can be up to around plus or minus 15 minutes. And there's two causes astronomically what's going on. It's got to do with the way the Earth rotates around the sun. The first is the elliptical orbit, or the eccentricity. It's not a perfectly round or circular orbit around the sun. It's slightly elliptical, and this causes changes in the speed of the Earth's rotation. So the Earth's orbit around the sun is not perfectly circular. At different times of year, Earth moves slightly faster or slower in its orbit, which causes solar days. This is from noon to noon by the sun to be slightly longer or shorter than the average 24 hours. So we're dealing with an average 24 hours on our clocks, our watches, not a true solar day. And the other one has to do with the axial tilt. That's why we get our seasons. Earth axis is tilted at 23.5 degrees relative to the orbital plane. Because of this, the speed of the sun's apparent motion along the celestial equator varies depending on where the Earth is in its orbit, altering how solar time projects onto your usual reckoning of hours. So we've got the two effects. We've got the eccentricity of the orbit and then the axial tilt. And from that we get what's called the equation of time. This is an equation that tells you to add or subtract. And this is a handy graph that you'll see a lot of places that it goes by the month, and so this tells you what to do, add or subtract. So in my case, I've got to subtract 3 minutes from September, about right here, and it's going to be a minus 3 minutes reading off the graph. So I've subtracted 3 minutes from my observations on the sundial. That's my first correction. Now another correction that I need to take into account is going to do the difference in the magnetic north from the true North Pole, and this has to do with where you're at. And so in some places, this is a North American map. There's maps for other parts of the world depending on where you're at, so you can pull those offline. I just did North America as that's where I'm at. And so I'm 2 degrees east. So my reading is in the central time zone, and here I'm going to be fairly close, but I am a couple degrees off. So you can see if you go to the west coast or east coast of the United States, it's way off. And other parts of the world it is too. So you need to take this into account. And there's graphs and tables online that will help you do that. So another correction I've got to take into account is since this is summertime in central time zone, I've got to add 60 minutes to my central daylight time. And so there's another correction which I'm going to go into just briefly in just a second. It's got to do with the longitude. And I'll explain that in just a second, but the net corrections is 49 minutes because I added 60 and then subtracted the 3 and the 8. Now I'll talk a little bit about this longitudinal correction. I didn't have to make this to the actual data because the British Sundial Society site takes that into account. Your longitude, your gnomon is adjusted slightly. So I didn't have to take that into account, but I want to just briefly mention that to you. And this has to do with the fact that these time zones, like I'm in the central time zone, so it's going to be at the 90th meridian right here. And depending on where you live in that zone, you're going to be off. And so it's about 4 minutes per degree. So that has to be taken into account. Like I said, in this reduction of date, I did not have to take that into account because the sundial was built with that correction in line. I had to enter my latitude and longitude into the British site, and that corrected for it in the design. So that's a great thing. So let's look at my first observation. The sundial read 7:55. This was early in the morning. So that we know the net correction is 49 minutes. So the actual time should be 8:44 according to the sundial. This is what I would read on my phone or my clock. But the actual time that my clock said was 8:32. So I'm off by 12 minutes. And sundials, unless you get a very precise, professionally made one, they're going to be off by several minutes. You can just count on that. And so this first reading was off by 12 minutes. So this graph shows, and there's my 12-minute reading off. This graph shows the actual clock time that I measured with my smartphone. And then this is the corrected sundial time that I added the 49 minutes to the actual readings down here. And you can see it just changes. The bigger part of the error is during the middle part of the day. And so you'll get a curve like this if you actually plot all this. Now this shows the actual residual measurements after the corrections have been made. And you can see during the middle part of the day I'm off consistently. And then the other parts of the day I'm off, but it changes. And sometimes we're just right on. So some of these observations are going to be exact, and some are going to be a fairly amount off, like I said, plus or minus 15, 20 minutes. Now, once I applied this correction for the end of day, the daylight savings time, the magnetic declination, I had to add 49 minutes to my solar measurements. And if you take the average of all those errors, less than 5 minutes. So if I was on an island and I didn't have a watch or a clock, if I could get plus or minus 5 minutes, that wouldn't be too bad. The residuals range from minus 18 minutes to plus 20 minutes. And so the pattern suggests some kind of alignment error, possibly the Neumann angle. It could be many things. I made this thing in my garage, and it was not made to military precision. So there's going to be some errors. But overall, it did a pretty good job. So the corrections bring the sundial readings close to the actual clock time. So that's what that's for. Well, I hope you learned a little bit about sundials and how to correct for some of the time differences. And if you did, give me a like, thumbs up, and subscribe to my channel. And thank you for watching.